Um, yesterday, yesterday we worked with transferring um, a complex number in rectangular form into a complex number in polar form. That was by taking r to be equal to a squared plus b squared under the square root. Okay, and we called that modulus, or the absolute value of z. Those are all notations that we talked about yesterday. And we also found theta by taking tangent inverse of your b over a values. Okay, where b is the complex, or sorry, the imaginary component of your complex number, and a is your real component of your complex number. Today, we're going to talk about how we can use those formats to quickly multiply complex numbers. If you remember we did one yesterday, but if you remember from college algebra or algebra 2, when you multiplied complex numbers, you had to FOIL them, right? And then incorporates eventually an I squared. You can change that to a -1 and move through accordingly. And even if I have to multiply maybe multiple complex numbers, more than 2, okay? How do we address that? Okay, so here is the way we go about doing this. Okay, it says multiplication, division of complex numbers. Let me zoom in a little bit for us. It says if two complex numbers z1 and z2 have these polar forms. Okay, and a lot of times we said yesterday this might be written as r1 cis theta 1. Okay, this might be written as z2 is equal to r2 cis theta 2. Okay, those are equivalent notations. Then if I want to multiply z1 and z2, okay, all I have to do is multiply the radiuses or the moduli, and then I have my cis, cosine, and plus I sine, but we add the thetas together. Okay, now that might also look like this. It might look like r1, r2 of cis theta 1 plus theta 2. Okay, those are equivalent notations as well. Okay, so multiplying complex numbers in polar form turns out to be a little bit easier than multiplying complex numbers in rectangular form. Okay, if I want to divide them, if you remember division of these two things, so if I had something like 2 plus 3i over 4 plus 5i. You guys remember how you divided those? It's kind of like how we divide radicals and stuff like that. We actually have to, not the reciprocal, conjugate. We multiply by 4 minus 5i, 4 minus 5i, and that will eventually alleviate your i's in the denominator, give you a rational number in the denominator, and then you'll be left with some i's up top. But in polar form, if I want to divide two complex numbers, I take their moduli and I divide them. Okay. Now it is important. Division is not commutative. Okay. So it is important how I'm dividing them. Does that make sense? So if it's z1 over z2, then it's r1 over r2, and theta 1 minus theta 2. If it was z2 over z1, it'd be r2 over r1 and theta 2 minus theta 1. Okay, so because division and subtraction are not commutative, the order is important. Obviously, z2 cannot be 0 because then you're dividing by 0, which is undefined in the complex plane as well. That is equivalent then, guys, to r1 over r2 cis theta 1 minus theta 2, if you want to write it that way. All right. So just kind of generically speaking, it says to multiply two complex numbers, multiply the moduli, add the arguments. To divide two complex numbers, divide the moduli, subtract the arguments. And it's that easy. Okay. When we have more time, maybe later, I'll give you kind of a visual of why maybe this makes sense to us in regards to the graphical aspect of things. So here's how we do it. Let's do a couple examples here before some of you guys take off. It says, let Z1 and Z2 be those things. Find Z1 times Z2 and find Z1 divided by Z2, okay? So we'll do Z1, Z2 first. All right, so Z1, Z2. The moduli, okay, so this is R1 and that's R2. Do you guys agree with that? Okay, so when I multiply those, we get 2 times 5. And then it'll be cis. And now I take my thetas, pi over 4 and pi over 3, and I add those together. Okay, so that turns out to be 10 cis. All right, now pi over 4 plus pi over 3 in the common denominator, right? So it'll be 12, so it'll be 3 pi over 12, and what, 4 pi over 12? So I get 7 pi over 12. Okay, and that turns into, then if I want to rewrite, so that's the final polar form. But if you're wanting to expand that, be a little bit more specific, you can go 10 cosine 7 pi over 12 plus 10i sine of 7 pi over 12. Okay. Now I'm interested just briefly here in seeing if we can evaluate this thing real quick. And because we should be able to see if we have the correct answers. If I take cosine, well, let's just evaluate 10 cosine. And the reason I'm using calculator is because 7 pi over 12 is some increment, some multiple of 45, so it's really not a nice value off the unit circle. So we can use the calculator here. So 7 pi divided by 12 would give me negative. So this thing is going to be negative 2.588. Okay. And then making that sign should evaluate it to 9.659 pi. Okay. If you think about, so that's polar here. This is rectangular. Okay. If we go back to these two things, obviously these are polar form. If they were in rectangular form, this would be 2 cosine. Oh, let's just do it. Cosine pi over 4 is radical 2 over 2, right? So this would just be radical 2. Okay. And now sine of pi over 4 is radical 2 over 2 as well. So this would be radical 2 times I. Does that make sense, everybody? Okay. Over here, okay, this is, cosine of pi over 3 is 1/2, correct? So you get 5 halves. Okay. Plus then sine of sine of pi over 3 is radical 3 over 2, correct? So this will give me 5 radical 3 over 2. 5 radical 3 over 2 times I. Okay. Those things are kind of ugly, right? Okay. If we use our calculator here, I think this will do it. Just clean everything up here real quick. If I take square root of 2 plus I times square root of 2, multiply that by 5 halves, so I'm just going to write it as a decimal, 2.5, plus I times 5 square root of 3. Put that thing all over 2. See what it equates to. Is that the same thing as what we've got here? Does that make sense to everybody? Okay. Now, would you guys agree that if these 2 points showed up in rectangular format, that foiling process and evaluating to get that is probably a little bit more involved than what we did here? Okay. All we did here is we multiplied two moduli and added two arguments. Okay. Now I did convert it, but that conversion is not a terrible thing to do. You just grab your calculator and type it in. Okay. Now, if these numbers are off the unit circle, don't grab your calculator because you can be exact then. That's kind of the process that you go through for this problem. If division is so much more involved in regards to these two things, if I want to divide Z1 and Z2 in rectangular form, I got to develop conjugates and that kind of stuff and multiply. So that is going to be even more time consuming. But I want to show and walk through the process for finding Z1 divided by Z2. Okay, so Z1 divided by Z2, that's R1 over R2. And then we'll go cis, and it'll be theta 1 minus theta 2. Okay, these are always in order, the subscripts are always in order of the division over here. So 1 and then 2, so everywhere over here it's 1 and 2, 1 and 2. So then I'm going to get Z1 divided by Z2 would be 2 divided by 5. And then I go cis, and now it'd be pi over 4 minus pi over 3. Okay. Again, that's going to be 3 pi over 12. And this thing here is 4 pi over 12. So it gives me negative pi over 12. And that's okay to write it that way. If you want to go 2/5 cis negative pi over 12. Okay, but negative pi over 12, maybe some people don't like that. Is that the same thing as 23 pi over 12? Can I add 2 pi to that argument so that it becomes positive? Okay, those are all options. Those might be things that WebAssign asks you to do in regards to your theta to make sure that everybody's on the kind of same page of what their answer should be. Okay, they could say make sure theta is positive, or make sure theta is between 0 and 2 pi, or something like that. Okay, and I just think GeoGebra has kind of a nice built-in feature here. I haven't messed too much with it, but I think I can go 2 cosine pi over 4 plus I times sine of pi over 4. That should give me, okay, so let's rename that thing Z1. So there's your Z1. And that makes sense. We found it to be, if you remember, we had radical 2 plus radical 2i, and that's exactly what those decimals are, is radical 2. Then Z2 we said is 5 times cosine of pi over 3 plus I times sine of pi over 3. So I get that. Okay. Now, like I said earlier, we already did Z1 times Z2. This is just allowing me to check to make sure we've done things correctly. And we had that earlier. But now if I do Z1 divided by Z2, I get that number right there, which should be this thing. If I type in that thing, let's go 2/5 times, okay, cis means cosine of 23 pi over 2, or sorry, 12, plus then I times sine of 23 pi over 12. And hopefully it gives us the same thing. And it does. Okay. So just using some technology there just to validate what we've done algebraically. Okay. Your TI-83 or 84, I don't mess around with those things too much anymore. In regards to using the complex components that they do have, I think you get second period on your, or second decimal point on your calculator, and will give you the I. Okay, and you can maybe mess around with a little bit, see if it does any of this stuff. So those are and GeoGebra might even have, I don't know, I'd have to do a little bit of research to see if it actually has like a quicker way of typing that in. Maybe I can type it in as sys or something like that. I'll investigate that and let you know. Does that kind of make sense on how to do those, though? It's not, you know, overly complex in regards to multiplying those out. A lot of times, though, when you do get them into this format, you remember this is r sys theta, sometimes they will want you to say, okay, what does that look like in rectangular form? Okay, because rectangular form, for us at least, is probably a little bit easier to graph in the complex plane than what this is in regards to graphing. Okay, however, in this form, the algebra should be a little bit more condensed, a little bit easier. Okay. Let's see here. All right. So that you see several examples in your homework about that. We can talk about those tomorrow if we have time. But that brings us into this guy named de Moivres. Okay. I talked about him yesterday, French guy from about the 1600s. Came up with this concept. Okay. And it's basically a repeated use of what we just did. Okay. I want to take 2 plus 3i times 2 plus 3i times 2 plus 3i times 2 plus 3i in times, as many times as I want to. Well, then eventually I'm going to take a bunch of r's that are all the same and be multiplying a bunch of r's together that are all the same. Does that make sense? Okay. So, give you an idea of what I'm talking about here. If I had, you know, 2 cis pi over 4, and I wanted to multiply that by 2 cis pi over 4, and then multiply that by 2 cis pi over 4, and I want to keep doing that, okay? Currently, I would have r being 2, or r1 is 2, r2 is 2, r3 is 2, so I have 2 times 2 times 2, right? Well, that's 2 to the third, isn't it? You would have cis, and you have theta 1 plus theta 2 plus theta 3, right? Well, they're all the same, aren't they? So doesn't that turn out to just be 3 times theta? Or in this case, because theta is pi over 4, 3 times pi over 4. Okay? Now, if this goes out in times, okay, so I don't know how many times I'm asking to multiply, maybe it's 10 times, maybe it's 20 times, whatever, it becomes whatever this r value is, raised to the nth power, n being the number of times I want to multiply this thing out, cis, and then I'm going to add that, and that together in times. Well, repeated addition of the same thing is just multiplication, isn't it? So whatever that theta is, I take it n times, and I get that thing, okay? And that is de Moivres' theorem, okay, or half of de Moivres' theorem, okay? So if our question is to, you know, I talked about this the other day, if I'm looking at 2 plus 3i, and I want to raise that thing to the, let's just say, just for convenience sake, the 10th power, that's a very elongated process. Okay, you're going to FOIL many times with that. Okay, so the best thing to do is to convert that. Okay, convert that to polar form, and then use de Moivres' theorem, which is going to basically just say you raise your r to some power 10, you take your theta and you multiply it by 10, and now you've got that complex number in polar form multiplied by itself 10 times, and then you change back to rectangular to see what that looks like. Okay, so do a couple examples here. I think you're going to pick up on this pretty quickly. All right. Now I'm using some numbers here that are just convenient for us because of the 1/2. So let's see here. Get rid of all this solution stuff. All right, so we're looking for 1/2 plus 1/2 I to the 10th. You do not want to do that algebraically. If you're doing that on a test or a quiz, you are going to waste precious time in writing this thing out 10 times, foiling, all that kind of stuff. So what we want to do, we're going to change this into polar form. Remember, polar form, your R value is that, And theta is going to be that, where this is your A and that 1/2 is your B. So I'm going to get, when I square that, I get 1/4. And when I square that, I get 1/4. So it gives me square root of 1/2, which we know rationalizes hopefully as radical 2 over 2. So there's my R value. Okay. This is going to be tangent inverse of 1/2 over 1/2, right? Well, that's essentially 1. So tangent inverse of 1 is at 45 degrees. I'm going to go pi over 4. Which if you want to go 45, that's fine. It's not a big deal. So now I know that this point here, what this really looks like, instead of 1/2 plus 1/2 I raised to the 10th in rectangular form, we can rewrite this as R cis pi over 4 raised to the 10th power in polar form. Now the benefit of that is I should be able to take and use the Moivres theorem, which says if I have R cis theta and I want to raise that to the nth power, it turns into R to the nth cis n theta. So all I got to do right here is take radical 2 over 2, radical 2 over 2, raise that to the 10th power. Okay, which that turns out to be kind of an ugly number, but whatever, it's all right. And then we go cis, and then pi over 4 times 10. Okay, so it becomes 10 pi over 4. Okay, does that make sense? Now you guys can evaluate, but radical 2 times itself 10 times is going to give me 2. I want you to think about it this way. Is this not, and this is the benefit of knowing some algebra. Radical 2 is 2 to the 1/2, isn't it? When I have a power to a power, what do I do with the 1/2 and the 10? Multiply them, so it gives me 2 to the 5th, right? Does anybody know what 2 to the 5th is? 2 times 2 times 2 times 2 times 2 times 2, 5 times? 32. So I get 32. 2 to the 10th is 2 to the 10th, 1024. Okay. And then cis, 10 pi over 4. Okay, think about 10 pi over 4. Is that larger than 2 pi? Because 2 pi is 8 pi over 4, isn't it? Okay. So can I reduce this down to 2 pi over 4? But what's 2 pi over 4? Pi over 2. Okay. So now 32, let's see if that divides into 124 or 1024. It does. Obviously, that makes sense, yeah. So I get 1 over 32. Cis of pi over 2. Now let's look at that. That's 1/32 cosine of pi over 2 plus 1/32 sine of pi over 2. Okay? What is cosine of pi over 2? Come on, guys. 0. That thing goes away. What's sine of pi over 2? 1. I don't have any of my I in there. So this gives me 1 right there. 1 times 1/32 is 1/32 times my I. So this thing should equate to 1/32 I. Okay? If you did that using the foiling process for 1/2 plus 1/2 I to the 10th, you would still be foiling right now. Does that make sense? And we've got the answer. Again, using something like GeoGebra, and guys, I'll let you use this stuff on test. I've said that before. But you're going to need to show me, obviously, the work here involved in finding the components for this. And I just hid that for some reason, and I can't get it back. There we go. 1 over 32i. And what I'm going to do here is just use GeoGebra to see if that makes sense. Okay, we had 1/2 plus 1/2 I, right? And we raise that to the 10th power. Gives me that number right there. And if I go out, see the rounding here. Okay, gives me that there. Okay, which is that the same thing as 1 over 32 times I. Does that make sense? Okay. You would not, though, guys, you would not want to multiply that out, okay? And that is actually a task that a lot of tests and quizzes will ask, is they'll say, okay, let's just do something like with the third power, because the third power is not ridiculous for you to FOIL, and they'll say, FOIL this by hand. And they'll say, go the long way, see what you get. And then they'll say, okay, now do it using the Moivres theorem, see what you get, and the hopes are that you recognize that they are the same answer. And even with the third power, the Moivres, if you were timing yourself, the Moivres process a little bit faster. Okay. A lot of times they'll use powers that they're not inconceivable that you could not FOIL, but you still would not want to. We can do the same thing. And we'll talk about this tomorrow with taking nth roots of complex numbers, okay? Meaning take complex numbers. This is something you've never done algebraically with rectangular components like a plus bi. You've never taken the square root of a plus bi or anything like that. You can now, okay? And that's what we'll get into tomorrow. Hopefully that gives you enough. And my hopes were, and I didn't realize that you guys were leaving for this trip this soon. It's my fault. I should have looked at that paper a little bit more closely. I was hoping to get through some more examples, but if in the event your homework's not due, at least this part of homework is not due tomorrow. So if we need to go over some more examples tomorrow, we can do that. We start thinking about time, guys.
Pardon the interruption, but anyone going on the field trip with Mr. Place, if you would please report to the lobby at the